There. This lesson is lesson 4.3, and it's all about predicting the direction of a reaction. If you haven't yet gone through lesson 4.2 and done the homework for that lesson, I highly recommend doing that before you attempt this new lesson. Today's lesson is very much based upon knowing what was going on in lesson 4.2. So today we're going to learn how to use something called Le Chatelier's principle to predict whether a reaction will proceed towards the right-hand side, the products, or towards the left-hand side, the reactants. This, of course, applies to reversible reactions. So far in this unit, every reaction we've worked with has already been in equilibrium. Today, we're going to learn what to do if a reaction hasn't yet reached equilibrium. We're going to learn how to predict whether the reaction is proceeding in the forward direction. So, how do we do that? How do we predict the direction the reaction will proceed in order to reach equilibrium? Well, we do it using the reaction quotient. The symbol we use for reaction quotient is Q subscript C, and then it's an expression that's exactly identical to the equilibrium constant expression, but its value is calculated using concentrations that aren't those at equilibrium. So here we're trying to figure out what's the reaction quotient for the general reaction uh, shown there. Well, our reaction quotient would be, and you'll have to excuse me, I'm writing with my tablet vertical. QC, my reaction quotient, is going to equal the concentration of product R to the power of C times the concentration of product S to the power of D divided by concentration of P to the power of A times the concentration of Q to the power of B. So again, just like the equilibrium constant, it's the products divided by the reactants, each to their own particular exponent. So once you calculate the value for QC, well, you can do that by substituting in the concentration of each substance into this expression. And once you do that, well, if your QC, your is equal to your equilibrium constant, then you know for sure that reaction is exactly at equilibrium. If QC is greater than the equilibrium constant, that tells you the numerator is large, meaning there's a lot of those reactants left over. And the concentration of chemicals on the right side is greater than on the left side. So the system would reach equilibrium by moving to the left. That tells you you had a lot of product. In order to reach equilibrium, you need to move to the left. On the other hand, if Q is less than K, then the system attains equilibrium by moving to the right. Hold on, I think all this makes a lot more sense if we use it in an example. So this chemical equation that I've got here is the chemical equation for something called the Haber process. It's used for the manufacturing of ammonia, and it's actually really, really important for the production of fertilizer so we can grow more. So in this reaction, we react nitrogen gas, hydrogen gas to make ammonia, and it's done at very high temperatures. At 500 degrees Celsius, the value for KQ for this reaction is 0.4. In our example, these are the concentrations that are present in a container. We're asked to figure out, is the mixture at equilibrium? And if not, which direction would the reaction go to reach equilibrium? Okay, so to do this, I have to write my expression for Q. Q is equal to the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 to the power of 3. Then I substitute my concentrations into my formula. So my concentration of NH3 was zero point 0.2. My concentration of N2 was zero point 0.1. My concentration of H2 was zero point 0.3. I plug all that into my calculator, and I find that my value for Q was 14.8. Now I have to compare my value for Q to my value for KEQ. That is greater than the value for KEQ. Well, how do I know what this means? Well, we know for sure that it's not at equilibrium because the value for KEQ is not equal to the value for Q. So we have to figure out which which direction this will go. So reaction, because QC is greater than KEQ, that tells us that we've got more of this than this side over here. As a result, the reaction will proceed by moving to the left. Sorry, excuse my terrible writing. Because QC is greater than KEQ, to the, and you can refer back to the slide before if you like to kind of solidify your thinking on that. Okay. So what happens to a system at equilibrium if the concentration of one of the reacting chemicals is changed? What would happen if we added more N2 or we added more H2? This is the sort of thing that happens all the time in manufacturing. Let's see what would happen here. So let's think about this chemical. If you were manufacturing ammonia, sorry about that. If we were using the process to manufacture ammonia, well, then we would want the ammonia from the chemical reaction, removing it. If we remove ammonia from the equilibrium mixture, then our numerator will decrease. That would result in QC being smaller than KE. When that happens, well, then our reaction proceeds by moving the equilibrium to the right, by producing more ammonia. This keeps happening as you remove ammonia. Similarly, if nitrogen was added, or hydrogen was added, or both were added, the system reestablishes equilibrium by shifting to the right. As long as pulled back constant, reestablished equilibrium will have the same KQ as the original. So the guy who came up with all of this was a French chemist named Henri Le Chatelier, and he did a bunch of experimentation and came up with this principle. The dynamic equilibrium tends to respond with relieve the effect of any change in the conditions that affect the equilibrium. Essentially, things shift back to reach equilibrium. Doesn't matter what you do, that's what happens. So, Le Chatelier's principle is set up to predict the way that a system responds to change. Pause our video here and take a minute to go watch the YouTube video that I posted on the card for this lesson. This really helps you get a good understanding of Le Chatelier's principle and what it means. Did you really watch the video? Okay, sent it. Go back and watch the video if you haven't yet. There's two posted up there, and they're both super useful in helping you visualize what's going on with Le Chatelier's principle. The next thing I want to talk about is the effect of ions on the equilibrium of aqueous systems. There's an idea called the common ion effect. If you have an equilibrium system that has a bunch of ions in solution, you add more of one ion that's already present, the equilibrium will shift away from that. It's exactly the same thing that happens if you increase the concentration of one of the reactants or the product. Temperature also affects the equilibrium. That second video that I asked you to go and watch was particularly helpful in understanding how temperature affects equilibrium. Remember that the value of your KEQ changes with temperature because the rates of forward and reverse reactions are affected. We can use the Chatelier's principle to predict what effect changing the temperature will have on a system when we know what the sign is for the enthalpy change. Here I've got an example. I've got sulfur dioxide reacting to produce sulfur dioxide, an oxygen gas. This is an endothermic reaction. It requires energy to happen. So I wrote this chemical equation with energy on the left-hand side of the arrow. So as this reaction proceeds from left to right, energy is absorbed and converted to potential energy. If you heat that system up, then you're adding energy to it. You're increasing the amount of energy. So you're going to shift the equilibrium away from the added reactant. If you decrease the temperature, then you're decreasing this amount of energy, and you would shift the reaction towards equilibrium and the reactant because that's what you reduce. So changing the temperature also affects the equilibrium, um, and it will respond exactly like um, changing the concentration of one of the reactants or the products. Okay, here I've got another example. What would happen if we heated up this reaction? Let's take a look at this equation if we write it with our energy as a reactant or product. First big question, is this an exothermic or an endothermic reaction? Well, the sign is negative, so we know for sure that this is an exothermic reaction. If I write this out, 2H2 plus O2 produces H2O. Well, if this is an exothermic reaction, then the energy term should be written on the right-hand side, exactly as if it was a product. So if we heat this up, well, then we are increasing this amount of energy. Increasing this amount of energy will shift our equilibrium to the left. Again, excuse me for writing. Shifts the equilibrium to the left, increasing the amount of H2 and O2. So anytime you have an endothermic reaction or an endothermic change, increasing the temperature will shift your equilibrium to the right. Anytime you have an exothermic change, increasing the temperature shifts the equilibrium to the left. Volume and pressure also affect things, particularly when we're talking about reactions of gases. When the volume of a mixture of gases decreases, the pressure of the gases has to increase. This kind of brings you back to grade 11 chemistry, and it might be a long time since you've thought about those gas laws. But remember that increasing pressure decreases the volume of a gas. Decreasing the pressure would allow your balloon to blow up bigger and increase the volume. Le Chatelier's principle also can be used when we're talking about pressure and volume. The Chatelier's principle predicts the equilibrium will always shift in response. Here I've got what happens when we've got a reaction of two gases. Again, the SO2, which is a gas, reacting with oxygen, a gas, to produce SO3 and some energy. So here I've got two gases reacting to produce um, one gas, but I've got 2 moles of the SO2 and only 1 mole of the oxygen, so 3 moles on the left hand side and 2 moles of gas on the right hand side. Because my volume of the container decreases, that means that the amount of pressure definitely will increase. So my pressure is going up. So now I've got more pressure, smaller space. There's less space in there for those moles of gas. Remember on the right-hand side, I only have 2 moles. On the left-hand side, I have 1, 2, 3. In order to compensate for this increase in pressure, the equilibrium will shift toward the side that has less moles of gas. Well, that's toward the side of the SO3. So what happens, we see that the equilibrium shifts towards making more of this SO2 pretty dramatically. On the other hand, as it does, you end up shifting away from the SO2. To restate this really clearly, anytime you reduce the volume of an equilibrium mixture of gases at a constant temperature, it shifts it causes a shift in equilibrium in the direction of fewer gas molecules. It will shift to the side with less moles of gas. Well, what would happen if there's the same number of gas molecules on both sides of the reaction? Well, then changing the volume or changing the pressure will not have any effect on the position of equilibrium. It will stay the same. So when we think about increasing pressure is the same as decreasing volume. If you're increasing pressure, if the added gas reacts, then the effect is the same as just increasing the pressure. If the added gas is inert, this is a little different. Your equilibrium won't shift. If the volume of the container expands when you add an inert gas, the effect is the same as increasing the volume and therefore decreasing the pressure of the reacting gases.